Welcome to a maths lesson all about probability. The question we have to ask ourselves is, can mathematics help us to predict the future? Well, what do you think? I think it's worth exploring, so let's go and have a look at what we're going to be doing in this lesson. Have you ever thought about, is it possible to see into the future? That would be amazing, to be able to recognize that something is going to happen before it actually happened. But is it possible? Well, people have dreamed about it for many years, but we're not sure that it really is possible. There's a big question mark around that. But what are the chances that you can guess or calculate the result of a soccer match? Well, if it's a certain soccer team, well, maybe you can look at what has happened in the past and from that try and make an estimation and predict what might the result be. But of course, there are always surprises and upsets, and even the team that wears yellow and black, they can lose sometime, or that other team that wears red, it can also lose sometimes. But you never know what's going to happen until it actually happens. And so this is the area of mathematics where we think about chance and what could happen. We call this idea probability, making some predictions based on some data. There are two things that we're going to look at today: the theoretical probability and then doing some exercises, some experiments. And you know, I love doing experiments. So let's just go and have a look at these. So as I said to you, there are two ideas we're going to be looking at. The idea of theoretical probability, how do we calculate it? And then doing some probability experiments. But before we get into those, let's have a look at some key words. We've spoken about the word experiment. An experiment in this context has a very particular meaning. It's an activity that is uncertain. We're looking at an activity where results are uncertain. The outcome of an activity or an experiment, that's what the result is. Now, let me be clear about this. If we're doing a whole lot of experiments, and these not necessarily throwing chemicals into a beaker and hoping for something to explode, but this could be a simple experiment of rolling a dice or flipping a coin, or it could be picking up numbers out of a box. All of those are experiments. The result of what we see at the end of the experiment, that's known as the outcome. It's also sometimes called an event. Right. Now, of all the events that take place, some of them might be things that we would like to happen. Some of them might be things that we don't like happening. So we have things that are called favorable events, those that we like to happen, and those that are not so favorable. We're not interested in those. So let's just recap there. Favorable events are the ones that we want. The outcome can be all the results. Okay. And we're interested in being able to look at the relationship between all the results and those that we really want to happen. And that's what probability is all about. Trying to establish the relationship between what we would like to happen and of considering all the possibilities of what could happen. Let's make it clear. And so in our definition here of what probability is, we're saying probability is the percentage chance of a favorable event taking place or in a favorable outcome or desired event taking place in an experiment. So be very careful about how we're going to represent this. We can represent it in different ways. Here is one particular way of representing what probability is about. We can say, of all events that we're looking at, some things are impossible, and then they have associated with them a probability of 0. So say, for example, if we had to think about some events like, let's celebrate Christmas on the 26th of December. Well, we'd say, no, that's impossible. It doesn't happen. Nobody does that. It's impossible. Perhaps even more impossible is if we thought about the event of the sun not coming up tomorrow morning. Well, we might not see the sun, but the sun will certainly come up tomorrow morning, as sure as anything. It's impossible for the sun not to come up. So I could say the probability of the sun not coming up is absolutely zero. On the other hand, I can say it's absolutely certain that the sun is going to rise tomorrow. I'm absolutely certain that on the 25th of December, the majority of people around the world are going to celebrate Christmas, because everybody sees on the calendar, the 25th of December is known as Christmas Day. And so it's not another day, it's that day. And so the probability of Christmas happening on the 25th of December is going to be said, yes, it's absolutely certain. It has a probability of 1. But you see, in between 0, the impossible, and the certain, there's a whole lot of question marks. And that's where we explore in probability experiments. So what's the probability of me flipping a coin and getting a head or getting a tail? Well, it's probably 50%. It's halfway between 0 and 1. Because there are only 2 outcomes. It could either be a head or it could be a tail. It's in the middle. We would say it has a probability of 0.5 or a half. And so as I've indicated there, here are some examples of probability experiments. I've already spoken about flipping a coin. Rolling a dice is another one. Picking up a card from a deck or using a spinner. Now, later we're going to actually see what a spinner is. This isn't a fidget spinner. No, I'm not giving you permission to play with a fidget spinner. This is a needle that is placed on a card that can spin freely and rotate, and it can stop at different points. We can have different segments around which it stops. We're going to do a very simple one and look at the probability of it landing on a certain colored region. All of these are experiments, and we don't know what the outcome is going to be until we've actually done them. So, don't get lost. Stay with me as we explore some probability experiments. Now, when we do this idea of probability, we've got to have some notation. And the biggest thing we're going to talk about in this little section is the idea of a sample space. And it's given a symbol S for sample. And it tells us it's all the outcomes are resting in the sample space. So everything that we're going to think about is there in that sample space for that experiment. It doesn't mean that we think about other experiments. We define our parameters very carefully and we keep them contained. So if we're throwing a dice, then we would say, what are the possible outcomes? What are all the possible outcomes? Well, we recognize that the dice is a cube and it has 6 sides to it. There are only 6 numbers. So the dice can either be a 1, a 2, a 3, a 4, a 5, or a 6. That makes up the sample space of the possible outcomes for rolling a dice. As I've said to you, flipping a coin, there are only 2. It's either heads or tails. Now, let's have a look at the next idea. What are the favorable outcomes? Now, this is your choice. You could decide that the favorable outcome or favorable event that you get really excited about is if you're playing a game and you roll a dice and it lands on 6. That's the one that you get excited about and you want to shout, yay, I've got a 6. I've managed to get the thing that I wanted. That's a favorable outcome. We recognize that the total number of favorable outcomes is represented by this notation. Favorable is the number n in brackets f, where the number of all the possible outcomes is given as the number, and then in brackets we have s. That s relates to the sample space. The f relates to the number of favorable outcomes. So if we are going to define and calculate probability, then we recognize the probability of a favorable outcome is actually defined as follows. It's the number of favorable outcomes possible. So maybe it's not that we just throw a 6. Maybe it's that we throw a number greater than 3. So it could be 4, 5, or 6. And out of all the possible outcomes, we can then say the probability of the favorable event is the number. Please notice it's not probability, it's the number of favorable things divided by the number in the sample space. So this is a very important formula and one that we're going to use quite often. And so what I want you to understand, in dealing with that particular equation or that calculation, there are more than one way of representing the probability. We can represent it as a percentage. We can represent it as a fraction. And that could be a common fraction where we say it's 1 out of 5, or we could say it's 0.2. It's still a fraction. So we can represent probabilities as a percentage, as a fraction, and here's another one that is very commonly used. We can represent it as a ratio of two things. Have a look here. We're saying it's a percentage, a fraction, or a ratio. So say, for example, my fraction was 1 out of 4. That is saying the ratio of the probability of a favorable thing happening out of the 4 possible events means it's 1 to 4 in a ratio. If we would convert that to a percentage, we would say that would be 25%, because it is equal to 0.25. So those are the ways of representing and measuring probability. I want you to make sure that you don't get confused in terms of, it's always got to be a percentage. No, it doesn't. It can either be a fraction, a decimal, a common fraction, or a ratio. It's all about the chance of something happening. Now, obviously, the closer that probability is to 1, if it's a fraction, the more chance, the more certain it's going to happen. The closer it is to 0, the less chance it's going to happen. So we need to be very clear and make sure that we understand when we read a probability what that's telling us, that we are certain or not so certain of something happening. I'd like to do a quick calculation with you, and I'll do a little experiment so that we can make sure that we've got things in place so that we can build on this. And so in my example, what I'm going to say to you is, if in a bag I have 6 black socks and 2 white socks, what is the probability of selecting a black sock? What's the probability of selecting a white sock? Well, you know what? We don't just talk about these things. We've actually got to do them, because probability is all about experiments. And so in this bag, look what I've got. I've got a white sock and another white sock. That's 2 white socks. And over here, count with me. That's a black sock. That's 1, 2, 3, 4, 5, and 6 black socks altogether. So into this bag, and I'm going to show you, there's nothing else in the bag. There's nothing else. You can see the bag is completely empty. Now I'm going to put these socks back into the bag, and what I want you to think about is, what do you think the probability is going to be of pulling out a black sock? Do you think it's going to be high or low? Let's have some fun. Let's predict. Well, what's the total number of possibilities that I could have? Well, I could actually have either a black sock or a white sock. So, in effect, the number of socks that I've got in the bag here, I could pull out 6 black socks, or I could pull out 2 white socks. So the total number in the sample space is 8 possibilities. And out of that, Let me see what I'm going to get. The number of black socks. Oh, there we go. There's a black sock. Why? Well, because there were 6 out of 8 for the black socks. So if I was to think about the probability, the total number of socks is 8. The number of socks in total is 8. The number of black socks is 6. So it's 6 out of 8, which is 3/4. So it's a 75% probability of choosing a black sock. Whereas out of choosing a white sock, there are 2 white socks. There are 8 socks in total. So 2 out of 8 is 1/4, and that is equivalent to 25%. Well, I hope you got that prediction right, and perhaps get your bag and see if it works. Ah, there's a white sock. Aren't I clever? I got it, just even though I wasn't sure it was going to happen. Don't be shy. Go and play a little bit with some probability and take a little break, and we'll be back to explore this a little bit more in further detail. Hi guys, welcome back to our lesson on probability. Remember, we're asking the question, can mathematics help us to predict the future? And this area of mathematics is called probability. Now, it's very closely linked to statistics, but we're just focusing on probability. And in the first little part of this lesson, we've established certain things about theoretical probability. Let's have a look at our concept map. So within our ideas of theoretical probability, we've got a definition for how to calculate probability. We can say the probability of an event that we would like to happen. So I'm going to say the probability of an event is equal to the number of times that event can happen divided by the total number of things that can happen, events in total. And I'm using S there to represent the sample of all possible events that can take place. So the probability is the event that we would like to happen divided by the total, and we can represent this as a percentage or as a fraction or as a decimal fraction, or we can even represent it as a ratio. So be very clear about this idea of theoretical probability. And so you might read or you might see in the newspaper or listen on a TV show that the probability or the chance of rain on a particular day might be 50%. What does that actually mean? It means of all the days and all the possible outcomes with these conditions, 5 out of 10 of them would have experienced rain in the past. That gives us the idea of probability, that it's predicting based on previous data that we can think that tomorrow there's a possibility or a probability that we could get rain happening. So you'll see that in the weather forecasts. But you can use this in everyday language as well. The possibility or the probability of an event taking place sometime in the future. And so we did a little experiment before the break, and you can do similar experiments. What we need to recognize is sometimes the experiment doesn't match with the theory. And so we need some new terminology when we're looking at actual experiments. So we're going to be looking at some probability experiments, and we want to make some definitions of things that we're going to be looking at in this situation. So when we're doing probability experiments, we call each experiment is known as a trial. So that trial could be, for example, tossing a coin or throwing a dice. Every time you do that, that's a trial. It's part of the bigger experiment. And we could do only 3 throws of a dice, or we could do 30 throws of a dice, or 300 throws of a dice. And each time we'll collect some data that will help us recognize what are the most likely outcomes. Remember that the result of a trial of a particular thing is called an outcome. It can also be called an event. It could be a favorable event, or it could be an unfavorable event. We're not worried, but it is an outcome. Okay, so the next idea we're going on to is this idea of relative frequency. Relative frequency is the number of times that an outcome occurs during experimental trials. And what we recognize that to get the relative frequency is not just to calculate the total number of times it happens, but to count it, divide it by the total number of trials conducted. So if I do 10 spins of a coin, of a spinner, and I find that the number of times that the spinner lands on blue, for example, is only 2, then the relative frequency of something blue coming up on the spinner is 2 out of 10. Now, I've spoken about the spinner without actually showing you a spinner, so let's hopefully get into that spinner right now. So there's our spinner. As you can see, this needle here is a free-floating needle, and it can spin. At the moment, it's on the blue square. We recognize it's touching blue. But we can let it spin freely, and it'll stop wherever, and it can stop at the blue square, it could stop at the red square, it could stop at the cyan square, or it can stop at the yellow square, or quarter segment. But, you know, so much for talking about little graphics. How about let's go and do it? But before we do that, I'd like you to think about some questions, because before every experiment, we must make some predictions. We've got to think about what the possible outcomes could be. Apply some probability thinking. So here are some questions I'd like you to think about. Can you calculate the theoretical probability that the pointer will land on the blue section after just one spin? What will the theoretical probability be after 4 spins? Got any ideas about what we could be doing? Do you think the theoretical probability will change, or will it remain the same? Well, think about it. Remember what our definition for probability was. We said it's the probability of a particular outcome, in this case the blue segment that we wanted to land on, is the total number of times that it lands on the blue divided by the total number in the sample. Remember, the sample space is the total number of possible outcomes. Okay, so I hope you've got an idea. For 1 spin, how many outcomes could there be? For 4 spins, how many outcomes do you think there could be? Think about it and see if you can calculate the probability. Now, if we're actually going to do the experiment, can you make a prediction about what you think on the first spin? Is the needle going to land on the blue, or is it going to land on another color? What are the chances? And if we did for 4 spins, what are the chances? Would you like to make a prediction? Take a piece of paper, write it down. How many of you think that there's a chance that it will land on the blue the needle will point to a blue section? What about a red section, or a yellow section, or the cyan section? Well, let's have a look and see. I think it's time to actually step into the laboratory and let's go and look at a real spinner. Now, this spinner is something that we can call up, and here it is, and I want to just reset because I was playing a little bit earlier. And we're going to recognize that we've got 4 possible outcomes. So it could be on red, blue, cyan, or yellow. And we recognize that we're going to calculate the experimental probability has already been calculated for us. They're equal in size and shape. And so this experimental idea tells us that there's a 1 in 4 chance of it landing on a particular square. And so in the table over here, we have been given that the theoretical probability is 25%. But if we actually let it spin, where do you think it's going to land? Let's see. Ah, it landed on the blue square. Isn't that amazing? Out of one spin, we wanted it to get to blue, and it got there. So the relative frequency, do you see? The relative frequency was, we wanted the outcome of blue, so that was 1. And how many spins was there? There was 1. And what's the relative frequency? I hope you can see it's 100%. It's not like the probability, because we've only had 1 spin. Let's add a few more spins, and let's see what happens. So I'm going to spin it again. Ah, it didn't land on blue this time. It landed on yellow. So the percentage of my theoretical or relative frequency has gone down. It went from 100% to 50%. And so it's getting closer to the theoretical probability. Let's see what will happen if we spin it again. This is the 3rd spin. No, another color this time, not blue. I really wanted it to happen to blue. But you can see what's happened to the theoretical, or not to the theoretical. The theoretical probability stayed the same. It was 1 in 4, 25%, but the relative frequency is no longer at 100. It's no longer at 50. It's come down. It's come down to 33%. 4 spins. Let's see what we'll get. Ah, look at that. It tells me that it's got a blue spinner. It's got a blue quadrant. So what are we back to? What's our relative frequency? We've got, out of 4 possible outcomes in our 4 trials, we've got 4 possible outcomes, and 2 of them are telling us it's blue. So blue's relative frequency is 50%. It's gone back up. It hasn't gone to where we wanted it to be, like the probability. But you know what? Let's speed up the number of trials. And so I'm going to change this and see what will happen if I make this spinner spin, say for example, 10 times. And if I let it spin and I let it skip to the end, look what's happened. The leaderboard has changed. We found that after a total of, if we add all of these up, which would be 7 and 4 is 11, 12, and 2 is 14. 14 spins so far. We've got yellow sitting on a 50% experimental relative frequency. Blue is only sitting on 28.6%, and cyan sitting at 14, and red is way back in the doldrums. But you know what, guys? Let's change this number. Let's change it. We're at 14. I want to get it to 100. So if I take that, I'm going to make it 86 spins. And let's see in 100 spins what will happen. So I'm going to let it spin, and I'm going to say let it skip to the end. And now it's done 100 spins. And what do you notice? Look carefully at these results, because the more times we spin the spinner, the closer the relative frequency is getting to the theoretical probability. Look, the blue is at 25 times that it's got to the blue count. So 25 out of 100 is 50%. It's exactly what our probability predicted. The cyan was also 25 times out of the number of spins. So it's also 25 out of 100. So it's also 25%. The difference is that it's not quite perfect for the yellow and the red. But you know what? I'm going to change it. I'm now going to make an extra couple of spins. And I don't know if it will do it, but I want to see if we can push it to make 900 spins. That will give us a total number of spins of 1,000. And we'll then be able to see if there's any correlation between the relative frequency, which is the actual events happening, and the theory, and see how closely those are matched together. So let's spin for 900, and let's hope that we're going to get there, and we're going to skip to the end to get our results. And what do you notice? We are getting closer and closer to the probability value. Our relative frequencies are very close to 25%. Some of them are 24.7%, some of them 24.2%, but they're getting closer and closer. So if I did another 1,000 spins, instead of just 900, let's do 1,000. Let's change it, make it, I've made it 1,000, and let's spin. So now 2,000, let's spin to the end. We're not going to wait it. And look, the values are getting even closer. So in doing this experiment and seeing that there's a difference between theoretical probability and relative frequency, I hope you can see that we can make some predictions, that our idea of the spinner is not so far-fetched. What conclusion can you make about the relationship between relative frequency and probability? Well, you see, it all matters about the number of times, the number of trials you go. So when we get lots of data, big data, then probability is a very good model for predicting what might happen. And so if we have to answer our question, can mathematics help us predict the future? All depends on how much data you've got. Think about it. We'll be back after this short break. Welcome back from your break. I hope you've been thinking about all those questions that I asked you about the relationship between theoretical probability and relative frequency. And I hope that you can see that we can use maths, possibly, to make some predictions about the future. It all depends on how big your data set is. It all depends on how many experiments you do. And so that's why I get excited about this particular topic of probability, because it's so relevant and it's so real. And even though we're doing silly little experiments like spinners and dice, it can apply to so many more things that we can see around us in the real world. And so we can make predictions, not just about the weather, but we can make predictions about the health systems, we can make predictions about climate, all if we collect data and we start to look at what the possible outcomes are and what the potential desirable outcomes that we're looking for. So let's have a look at our concept map again. And just to remind you, we have focused quite a lot on theoretical probability. And so you should know by now the probability of an event that we would like to take place is the number of times that event can happen divided by the number of total events that could also happen in a particular situation or scenario. Then we did some real experiments with a spinner. And what we recognized here is the key word is relative frequency. And you need to be very clear that relative frequency is very similar to probability in the sense that we can say relative frequency is equal to the total number of outcomes that we've got, that we've done in our sample. So these are the number of things that we're wanting, divided by the total number of trials. So that's the total number of trials, not the total sample space. So you can see we can do many trials. The more trials we do, the closer we get to the theoretical probability. So what I thought we would do in this little last section is to try and combine these two ideas by looking at a very simple experiment and use it to explain those terms and make sure you've got them. So let's talk about rolling a dice. Now, I'm sure you've all seen a dice. You know that it's usually a plastic cube and it has 6 sides, so it has 6 numbers on each of the sides. And so the first question is, what is the sample space for rolling a single die? We say the singular for dice is die. It doesn't mean fall over, okay, and not breathe. A die is just simply one of those cubic things that have numbers on them. Okay? So please be aware of that. So what is the total number of sample space? It doesn't depend on the size of the die. It is asking you about the numbers in the set that we can have on the side of a die. So the sample space is made up of these numbers. It could be a 1, it could be a 2, it could be a 3, or a 4, or a 5, or a 6 for this particular type of die. Now, if somebody said to you that they rolled a die and they got 8, could it be in this sample space? Well, no, it can't be this type of die. This type of die only has those 6 numbers. 1, 2, 3, 4, 5, and 6. Can't be 0, can't be 10. Now, there are die that are able to have those sort of numbers, and they play them in all sorts of games, but we're talking about a conventional die. And we recognize that there are only 6 possible answers from any trial or any experiment that makes up the sample space. Be very clear about this. The number in the sample space, that's the sample space as I've drawn it out. The number in the sample space is indicated as 6. So there's a difference between showing you all the numbers, the set of numbers that are possible, as compared to counting the number of options there are in the sample space. Be very clear about the difference between those. But I had asked, what is the sample space for the rolling of a die? And that's the sample space given as a set. The set, we use a curly bracket, and then we list the numbers. There are other ways of doing it as well, and we're going to see about those a little later. Now, let's look at the next part of the problem. And the problem is, what is the probability that when you roll a die, it lands on the number 4? Now, guys, this isn't that difficult, because actually we've only got one outcome. So it's really not difficult to see that the desired outcome here, the favorable outcome, is going to be the number of favorable outcomes. The number of favorable outcomes is for the number of 4 to be the answer, favorable 4. There is only one. There's only one possibility of, this isn't a fancy trick die that has 4 painted on 3 of the sides. No, it's got a number 1 on one side, a number 2, and so on. And so there's only one favorable outcome. And so if we were to recognize that there is only one favorable outcome, but the number of possible outcomes out of the sample space is 6. So what's the probability of us getting a 4? The probability of getting us a 4 is going to be the number of getting a 4, the number of possible ways of getting a 4, and the number in the sample space. And if you do that, you'll see it's 1 out of 6. Now, we can leave it as 1 out of 6. We could even say it's a ratio of 1 to 6. We could also calculate the percentage, and that's what I'm going to do here. I'm going to say, let's get our calculator out, and we're going to say 1 divided by 6 is equal to 1/6. We put it into a decimal, 0,1666, and it carries on and on and on. We have to round it off. Often they ask you to calculate to a certain number of decimal points. In this case, if they said 2 decimal points, we would say it's 0,167 as a decimal. But if we wanted this as a percentage, what would we do? That's right, we'd multiply it by 100. So we're going to take that, multiply it by 100, and if we were then to make sure that we do the 100, we'll get that, and as the answer, it's 16,67%. So this is exactly the same as 16,67%. That's the probability. We've now shown that we can use different formats to get the probability. Guys, there's one last little thing that I want to tie together. Is it always going to be 16%? 16,67%? In reality, is that what's going to happen? Well, we're not too sure. We know if we increase the number of experiments or trials, then relative frequency will get close to the probability. It could be bigger or smaller than the relative frequency, but, the relative frequency could be bigger or smaller than the probability, but they'll get closer and closer depending on the number of trials. But here's some data that we've got that we were given for a particular experiment. We're told that a die is rolled 48 times. Now, that's quite a lot of times to roll a die. And in the counting of the number of times the die has been rolled, the number 4 appeared a total of 5 times. Okay? So they say to us, what is the relative frequency of observing the die land on the number of 4? And you're asked to give your answer to 2 decimal places. So please don't get confused. When they ask for relative frequency, they're not asking for probability. The calculations might look similar, but they're not identical. So please be very careful that you understand and that you give your appropriate notation when answering. So let's go and take the data down and make sure that we've got it right. So if we say relative frequency is going to be the total number of trials, and we're going to divide that about the number of outcomes. So the number of times that it got to 4. Because that's what we're really wanting. We're wanting to find what's the relative frequency in this experiment, which had 48 trials. How many times did it get onto 4? Well, I've given you away some answers. The number of trials was 48. So the total number at the denominator here is going to be 48. The number of times that it landed on 4 was 5. So we get that the relative frequency of this little experiment is 5 out of 48. Now, guys, we can leave it as 5 out of 48, but the question didn't say that we should do it. It actually gives us an instruction. And here's a very important thing. Whenever you're doing a maths problem, you've come to an answer and you think, yeah, I've got it. Just go back and read your question, because in the question, look what it says. Write your answer correct to 2 decimal places. So it means calculator time. I've got to get out the calculator and do that calculation. So here we go. Remember, that was the probability. Now I'm going to use the calculator to work out the relative frequency. I'm going to say 5 was the number of times that it landed on 4, and I'm going to then divide this by 48. And I'm going to say 5 divided by 48 is equal to 5 out of 48. No big surprises there. But look what it says this is in terms of a number. 0,10416. Now I need to write it to 2 decimal places. So remember, I look at the 3rd decimal place here, and the 3rd decimal place is a 4. So be very careful that we're going to write this as an answer of 0,10, because I'm not going to round up. So let's just make sure we're in the right place to give our answer, and we're going to say that the answer to this, correct to 2 decimal places, is 0,10. What do you think it would be if we were asked for a percentage? Instead of a decimal place correct to 2 decimal places, what would the percentage be? Well, I don't think it's that difficult. We have to multiply that by 10. So the percentage, in terms of relative frequency, the percentage relative frequency would be 10. And if we used the decimal places as well, then you would be able to see it would be 10,4 0.42. We'd round up the 1 to a 2, and we'd be able to say 10.42%. That would be the percentage of the relative frequency. So guys, can you see that when we did the calculation for the probability, it wasn't that this wasn't the same. It was 16%, where here it's only 10%. What's that indicating to you? Well, I hope you can see that 48 isn't a big enough sample space to allow the relative frequency to get close to the theoretical probability. We'd have to do a lot more trials. And if you do a lot more trials, overall, you'll find that the relative frequency will get closer and closer to the theoretical probability. So let's just wrap up everything that we've done during this particular lesson, because I think we've explored some interesting ideas, and perhaps we're in a situation where we can answer our big question. But let's quickly go through a few ideas in our summary. So what is probability? If you had to use an everyday word could be chance. Now, what is the chance of something happening? It could be absolutely certain. Then you would say the chance of that happening is going to be 1. If it's impossible, then the chance is 0. The probability would be 0% of that happening. We define probability as the total number of favorable outcomes divided by the total number of possible outcomes. We've defined that very carefully. We've defined the formula for probability of a particular thing happening as the number of times that A would happen divided by the number of things in the sample space. And in a similar way, we've calculated relative frequency to be equal to the number of times that A happens divided by the number of trials total. We recognize the more trials we do, the closer those two numbers get together. And so I want you to make sure that you construct your concept map and remember these two things. When we're doing probability, always think about theoretical probability and experimental trial. Don't go away. Make sure you join us again the next time we have an opportunity to explore this wonderful world of probability. And perhaps one day we'll be able to answer the question, can maths help us predict the future? I hope you'll be part of the answer too.